So I have this starting point. I'm going to draw my starting point right here, and it looks like it's 5 to the right. So I'm going to go 5 to the right. And then instead of going further to the right or back to the left, I'm actually going up. So when I draw my vectors, I draw them tip. So I have the tip of one vector is the tail of my second vector. And I'm going to go up 10. Now again, I don't have any units, so that's okay. Now, drawing my resultant is always the same process. So before, when I drew my resultant, it was from the start to wherever I ended up. And that's what I'm going to do here. The start was there, the end was there. How long is my resultant in this particular example? Or can you think of a way I can calculate the length of that arrow? Now, direction is going to be a little bit difficult to describe because I'm kind of going up and to the right. You could say something like that, but it's kind of, probably a grade 11 concept. We use the Pythagorean theorem. You're right, Abby, we do. So we have a right triangle, if you can imagine that. There's our little right angle in the bottom corner. We have a right-angled triangle. We know that we can figure out any missing side on a right-angled triangle as long as we have 2 additional sides. So I'm going to go a squared plus b squared, c squared. It doesn't matter what a and b are. I'll call a 5 because that was the first one I drew. A squared, b squared is c squared. So I'm going to have 25 plus 100 is equal to c squared. Add those together. And then I'm going to take the square root of both sides. And I don't know what the square root of 125 is off the top of my head, but I do have a calculator that has that information for me. So I'm going to take the square root of 125, just plug it into my calculator, and it tells me that that is 11.18, so we'll just call it 11.2. Now, I'm hoping you guys are experts with the Pythagorean theorem by now, but if you're not, that's okay. So we haven't done any really difficult math in a while. So the beauty of me teaching you both math and science is that I know we use the Pythagorean theorem an absolute ton of times in math. So I'm confident that most of you guys are okay with that. I could be wrong, but I don't think I am. So there you go. That's how you're going to do these questions. I'll just give you, I don't know, there's a few questions, 3 questions there. I'll give you a few minutes to do each of those, and then we'll see what type of answers you ended up with. The last one's a kind of a tricky one. See if you can figure that one out. If you follow the same steps that we've been doing, you should be able to do the last one. Can we give a direction? That's a good question. Not in grade 10, you won't need to. The direction, we usually use kind of cardinal directions to describe it. That would actually be, what would that be? That would be north of west. But we're not going to calculate the angle or anything like that. So more of a grade 11 concept. But if you can use the Pythagorean theorem to find the length of the resultant, you're doing great. That's kind of where we want to end this now. So just give you, 5, 6 minutes. No, you probably won't need that much. 5 minutes, a bit generous, to do those last 3. And the last one's tricky, but I think you guys can do it. So I'll give you a couple seconds to do those, and we'll come back and we'll talk about them. All right, I'm excited to see which who got the last one. What about the second one here? I kind of jumbo sized this a little bit, so I'm just going to zoom out a bit. The second one here. Did anybody get an answer for the second one? I'll definitely go over all of them. I'm thinking the second one's pretty straightforward because it's really similar to the first one, but the resultant will just be in a different sort of direction. So let's 11.2, perfect. So the second one, B here, is instead of going to the right and then up, I'm going to go up and to the right. Which ends up being the exact same question. So I'm going up 10, and then I'm going to the right 5. And the resultant is exactly the same. It's kind of like if I told you, go forward 5 meters and then turn left, or if I say, hey, go left 5 meters and then go forward 10. You're going to end up at the same spot. So both these are the exact same. So that's A and B. C is a little bit different, so I'll do that one real quick. Maybe some room over on the other side. We'll call this guy C. All right, so I'm going to start here. I'm going to go up 10, and then I'm going to go to the left 10. Does anybody have a number for a resultant for letter C? What I'm calling C? So I started here and I went along there. Taylor got 14.2. Does anyone agree or disagree with that? I'll break out my Pythagorean theorem, and then if anyone wants to agree with that. So we have 10 squared, and 10 squared is 100 and 100. C squared, 200 is equal to C squared. And then I take the square root, both sides. Square root of 200, I'm going to just trust you guys. I'm not even going to break out my calculator. 14.1 sounds good enough for me. So this resultant is 14.1. Perfect. Everyone's on the right page. Well, everyone who's written something in chat, that's a good sign. This last one is tricky. It's all kinds of tricky, but I'm thinking if we follow the rules, we can do it. And of course, we've never drawn 3 arrows together yet. And now I've given you 2 directions to deal with, so it's kind of really complicated. So let's go. Let's see how we do. I'm going to start here, and I'm going to go down 5. And then I'm going to write in a number there, 5. And then I'm going to go to the right 5. And then I'm going to go up 10. And I draw my resultant. Is the last one 7.1, or is it not a triangle? We can make a triangle out of it, and you can always do that. So my resultant is going to be from my start to my end. I don't really like that arrow. Try that again. There we go. All right, so what I'm going to do is I'm going to make a triangle out of this thing. I'm going to draw in some like dotted lines here just so you guys can see where my triangle is. There we go. Got a little right angle here. So the base of my triangle is 5. What about this little bit here on the side? I know it's not 10 because the whole green arrow is 10. What's just that little bit that I have up at the top there? How long is that? Well, I went down 5 and then I went back up 10. So this little bit in here is 5. Perfect, Taylor, you got it. All right, so I can write in a 5 here. So if I have my Pythagorean theorem, I kind of have to decipher a little bit where my triangle actually is. I'm just kind of adding one in there. So I'm going to get 5 squared plus 5 squared, 25 plus 25, c squared, 50 is c squared, and then I'm going to take the square root of both sides. Square root of 50 7.07. So Ava had it. We'll call it 7.1. So well done, Ava. That was a hard one. How did we do on that one? Did a few of us get it? Did we miss it? It's kind of weird how we draw it. Another way you can do it is you can do all the ups and downs first, and you can do all the lefts and rights second, and then you can get all your lefts together and all your rights together and figure out what the resultant is going left, right, and then you can figure out all your resultants going up, down, and then you can make a triangle with those and then find your resultant. It's the same process. Sometimes it's even easier to do than what we've done. Okay, well, that's good to know. Because obviously, Anna, it's the first time you've seen something like that. So if you think, you kind of understand and can follow along, that's good. No worries, Taylor. Glad you're back. All right, there's a couple more sort of idea things that I want to go through, and then we'll do a few more examples. And then we will finish off. So I know I usually do a break after about an hour, but I'm thinking we can just kind of power through this. If I'm not mistaken, there's only a few more examples and then we're done. So we'll just, instead of, dragging out the morning, we'll just finish a little bit early. All right, so we're going to talk about some more vocabulary words. So far we've talked about distance. We've talked about magnitude, direction, scalars, vectors. These are kind of all words, resultant, all words that you've heard before but never really seen in this context probably. And we're going to make it, I don't want to say confusing, but we're going to use words that you've kind of always used to mean the same thing, but in physics, they mean different things. So we're going to talk about distance and position. And we're going to have a few sort of words that pop up that you're like, well, I've definitely used that word before, but now it kind of has a specific meaning. So distance is a scalar, meaning it doesn't have a direction. So that was kind of like going back to my house is 13 kilometers from the school. That's a distance. There's no direction associated with it. It'd be really difficult for you to find my house just knowing it was 13 kilometers away from the school. So the example here, a person ran 400 meters. There you go. That's a distance. I know how far they ran. I don't know where they ended up. I don't know what direction they ran, but they ran 400 meters. For all I know, they did a lap of the Apple Bowl, 400 meters. They started where they finished, or they could be 400 meters away. I just have no idea. That's a distance. A position is a distance with respect to another thing. So this is kind of like the resultants we've been drawing. We can say, your position is so far away from the Apple Bowl or something like that. So example, the school is 3 kilometers east of my house. That's easy to understand. 3 kilometers is how far you've gone, which direction? To the east of your house. That's kind of where we're going with distance and position, why they're different. So SI is Systématique Internationale, French consortium, does all the units for all of the world, and distance and position are both measured in meters. The only difference between them is that position will have a direction associated with it. This is not in the data booklet, the learning guide. I didn't print it off. I just looked at it quickly, and it seemed like it was kind of one of the learning guides where you just kind of go and some of the definitions kind of pop in and out, and there's some examples that maybe aren't there and are there. Is anyone else having some issues with that, or are we okay in terms of the learning guide? Is anybody else finding this stuff in the learning guide? Maybe if you had a page, you could throw it into chat or something like that. I didn't bring the learning guide with me. I don't even think I put the learning guide into OneNote, which I usually do. Nobody's chiming in, so everyone's asleep, I suppose. All right, so there's a little image down here at the bottom. I just want to talk about it real quick and then, okay, thank you, Shayna. So it's not just you, Taylor. It's definitely not in there, which is okay. You just take it in. All right, so let's say your house and the store were perfectly west and east of each other. So let's say I was at my house and I drove to the store. What is my distance I've traveled when I'm at the store? Oh, I have a laser pointer. Let's use that. What is the distance I traveled? So I started at home and I ended at the store. What's the distance I've gone when I'm at the store? And what is my position when I'm at the store? What do we think? Are my distance and position the same thing when I've gone from my house to the store? Or are they different? So distance. Distance first, 10 kilometers. That makes sense. I've gone from here to here. That's 10 kilometers. That's a good distance. And if I were to talk about a position, Abby, I think that's what you're referring to. It's 10 kilometers east. Now, we could be even more specific. 10 kilometers east is fine, but you could say 10 kilometers east of my house. Perfect. Okay, now I've bought my groceries at my store. I've driven back home. So how far have I traveled? What distance have I gone to go from my house to the store and then from the store back to my house? What's my distance traveled? And when I'm at home, what's my position? That's a bit of a tricky question, my position when I'm at home. So, Taylor, you've written in a position there, 10 kilometers west of the store. That's good. What's my distance traveled, though? How far have I gone? And is there another way to represent my position? Do I have to say 10 kilometers west of the store, or can I represent that a different way? Those are some tricky questions for a Monday morning. All right, so imagine I started at home, drove to the store, went back home. My distance traveled is 20 kilometers because it was 10 kilometers to get from my house to the store, another 10 kilometers to get back. So 10 and 10 gives me the 20. My distance travel is 20. When I talk about a position, I could say I'm 10 kilometers west of the store, or I could say I'm 0 kilometers from my house, which kind of is a really strange way to write it, but it's true. I'm giving you a position. How far am I away from something? If I left my house, drove around town, and then ended back at my house again, how far am I away from my house? So a position just needs to have, a distance away from something. So I could say, lots of different ways to represent the same thing. So it's a bit of a weird sort of idea. All right, so those two we looked at before were distance and position. Now we're going to talk about distance and displacement. Now again, two terms you've probably heard about, but now have new meanings. So displacement describes the straight line distance and direction from one point to the other. And displacement is equal to the final position minus the initial position. Displacement's the change, and we'll look at a different way to describe that here. But this kind of definition of displacement, displacement is equal to the final position minus the initial. This is a really complex, confusing way to describe displacement until we actually get into the next unit when this sort of definition will make more sense. But for now, it's just kind of a bit strange. So we'll talk about it a little bit, but don't be too overly concerned about it. Some questions here. If you start at your house is the most correct way to say 0 kilometers from the house. I wouldn't say that there's any more correct way than another. They're all sort of relative, right? They're describing the same thing, but just in a different way. I could say, if I was trying to describe where I am, I could say I'm not 10 kilometers, I'm 5 kilometers south of the mall. You'd know where I was. I could say I'm 300 kilometers northwest of Vancouver. Northeast of Vancouver. Makes more sense. They're both describing my position with respect to something. They're both correct. Not one is more correct than the other. So usually we'll have a picture. We'll have some sort of reference point. In the previous example, we had the house and the store. So you can use either one of those. Now, we're going to end up seeing a few pictures like the one here, where they give you a distance law on the bottom, and then they have different times sort of in there to figure out what's going on at each of those points. Sorry, Abby, I just saw that you asked a second question here. So displacement could be less than distance. It can be, yeah. Think about it this way. If I started at my house, I drove around town, maybe I went out to Tim Hortons to get some coffee, and then to save on foods, to buy some groceries, and then went to the dog food store to grab some food for the dog, back home. How far did I go? Well, my distance was, maybe 5 plus another 5 plus another 5. So I traveled maybe 20 kilometers on that trip. But what was my position? Well, I started at the same spot, or displacement, I should say. My displacement, how far am I away from my house? Well, I'm 0. I started at my house and I ended at my house. My displacement is 0 meters. But the distance I traveled was 20. So this is why it kind of gets a little bit confusing. Depending on where I go, my displacement and the distance could be the same, or they could be different. Just depends on how far you are from where you started. Generally speaking, though, displacement's going to be smaller than distance. Generally speaking. All right, let's jump back. Did I lose it? Did I just completely lose it? There it is. All right, so if we look at, can I do number 10 on page 2? I can. I don't know what it is. I'll have to find it and load it, but I can for sure. I'm just going to finish this off. It might even come up in the next few examples there, Taylor, so we'll get to it possibly. And if I don't, then I'd be happy to do it. So this little fella here is skateboarding. At 0 seconds, he's at 0 meters. 2 seconds later, he's at 2 meters. And then 5 seconds after that, he's at 7 meters. So we can describe his distance traveled. In 2 seconds, he's traveled 2 meters. In 5 seconds, he's traveled 7 meters. And we can describe his displacement. How far is he away from where he started at 5 seconds? Well, he's traveled 7 meters. What if I wanted his position or displacement from the fire hydrant to the sign? How far has he gone from the fire hydrant to the sign? I don't have to always talk about the tree to the sign. I could talk about from the fire hydrant to the sign. What is his displacement between these 2 points from the fire hydrant to the sign? Well, he started at 2 meters and then he ended at 7. So how far did he go between the fire hydrant and the sign? Well, that was 5 meters. So his displacement from here to here was 5 meters. What about from the tree to the sign? Well, that's now 7 meters because we started at 0 and then he went to 7. What are you really doing when you're calculating that? You're actually doing subtraction. And what I mean by that is you're saying, okay, he ended at 7 and he started at the tree at 0. So 7 minus 0 gives me 7. But if he started here and I want to know his displacement from the fire hydrant, well, he started at 2 and he ended at 7. So in your head, you're going, okay, well, that's 5 meters because each one of these is 1, 2, 3, 4, 5. Or you could go 7 minus 2 and you could end up with 5. So in your head, you're probably doing subtraction even though you're not really. Let's just see what is left here. All right, I'll do a couple more and then we'll just call it. It's an hour and a half. It's been a long time. All right, so let's do a couple of these examples and then we'll see how we're feeling, and then we might have to finish some of this tomorrow. All right, that's not where we are, not where we are. There we are. All right, distance versus displacement. We'll do a few examples. And the one in the notes here is a car drives 3 kilometers north, then 2 west, then 3 south, then 2 east. What's its distance and what's its displacement? Now, I'm a very visual person. When somebody gives me directions like, hey, go this way and then that way and then turn it this and go there, it kind of just goes in one ear and out the other. I can't process things through audio. I need to see them written down. And in my experience, students do very well when they draw pictures. So I've written it giant letters here at the bottom. Hint, always draw a picture. So do that. Draw a picture. When I teach Physics 11, I give students a mark for drawing the picture. I'm not talking like, do you have beautiful flowers and is your butterfly's wings symmetrical? Not things like that. Just arrows and dots. That's what I'm talking about here. So, it's similar to the learning guide? All right, well, we'll just go through it and we'll see how we go. All right, so like I was doing before, I was drawing pictures with arrows, and I'm going to continue to do that. So I'm going to have some starting point. Let's see if I can get this all in here. A car drives 3 kilometers north. So here's my start. Might regret writing that there. So I go 3 kilometers north. So north is up. And then I go 2 kilometers west. And then I go and then I go 3 kilometers south, so I'm back to there. And then 2 kilometers east. What is the car's total distance traveled and the displacement? Whew. All right. Distance is how far I went. So this is kind of like if you've driven a car recently or if you've looked at a car. You have something called an odometer on your car. And your odometer on your car doesn't care if you're going forwards or to the left or the right, you turned here, you turned there. It just counts up. The wheels are spinning, the odometer is counting up. That's what distance is. How far did you go? So in this case, the total distance traveled was, I started and then I ended at the same spot, which was a little bit inconvenient, but we'll figure it out. So I went 3 kilometers. And then I went another 2 kilometers. And then I went another 3 kilometers. And then I went another 2 kilometers. So how far did I go in total? Well, 3 plus 2 is 5, plus another 3 is 8, plus another 2 is 10. So my distance traveled was 10 kilometers. That's how far I traveled. That's the odometer reading on your car. You went up 3, you went left 2, you went down 3, you went to the right 2. My displacement, maybe I'll do this in green, is how far am I from where I started? So from the beginning to the end, from my start to my end, how far am I away from my starting position when I finished? The displacement is the same as the resultant. They're the exact same idea. Yep, they will mean different things. The resultant, we can talk about the resultant in more than one dimension, so like we can go up, down, left, right. Generally speaking, displacement will be on like a horizontal line sort of thing. So how far am I from where I started? If I start and end at the same spot, I guess kilometers is the units we were using. So the displacement in this question is 0. My distance was 10, but my displacement was 0 because I started and ended at the same spot. All right, maybe we'll just do this one and we'll call our day there. A child walks 3 meters north, 7 meters south, 2.5 meters south, and then 5 meters north. What is their displacement? All right, here we go. I'm gonna start here at the blue dot. I'm going to do it step by step. When I say draw a picture, I don't need to draw the child and the trees that are around him and the grass on the lawns that he's passing. I'm just drawing arrows and dots. So a child walks 3 meters north, and then he walked 7 meters south. This is why it's important to try to draw your diagrams roughly to scale. It'll make your life easier in the long run. I'm gonna run out of room there. That's 7 meters. And then he walks another, or she walks another 2.5 meters south. So 7, that's 2.5. Make sure to include my units. And then 5 meters north. What is their displacement? So how far, displacement is how far are they from where they started? So displacement's kind of like from here to there. What is that distance? What do we think? This is my end point here where I ended up. This is where I started. What is the displacement? How far am I from where I started? Is there an easy way to do this? Anyone think of it? There's, I guess there's no real right way to think about it, but can you do 3 minus 7 minus 2.5 plus 5? What do you end up with there, Abby? Let's check it out and see if it works. And then maybe if somebody, I'll try to like dissect the diagram. So Abby suggested anything going up is positive, anything going down is negative. So 3, then we went south 7, then south 2.5, and then north 5. What do we end up with there? I'll maybe kind of look at the diagram really closely here. So I went up 3 and then I went down 7. So that's kind of I basically have lost, I guess I've gone down 4 here. Going down 4, because that is what's left, and then I've gone down another 2.5, then I've gone up 5. So I'm going to think of it as going down 4, and then down another 2.5, and then up 5. So I'm going to go down 4, And I'm going to go down another 2.5, so I'm going to add 2.5 to that. Then I'm going to go up 5. So if I go down 4 and down 2.5, that's 6.5 I've gone down, and then I've gone up 5, so I'm going to subtract 5, and again I'm up with 1.5 meters from where I started. If I go 3 minus 7 is negative 4, minus 2.5 is negative 6.5, plus 5 is 1.5. So this is negative 1.5 meters, and that's the same thing I got here. We end up with these kind of like different signs. So what's going on? Well, mine, I didn't really indicate a direction, and here this negative sign is actually indicating a direction for us. That's why we ended up with that negative sign. So in my diagram, it's easy to see that my arrow is pointing down. That's what this 1.5 is referring to. In my calculation, if you just do it like you guys chose to do it, which was completely fine, you do end up with a negative, which just means in this particular question, it's going south or down. So I could write 1.5 meters south or negative 1.5 meters. They both mean the same thing. And yes, that's how I would suggest you guys do it. Why do I insist you draw a picture though? Well, if you were to go 3 minus 7 minus 2.5 plus 5, you end up with negative 1.5. What does that really mean? If you've drawn a picture, you can see that you've started here and then you've ended just a little bit below where you started. So it's really obvious in the picture to figure out exactly what's going on. So that's why the picture is important, and the picture goes along with the math. If you want to add your norths and souths, or add your norths, add your souths, then take the difference between them, that's fine. That is how you do the question, but the picture adds clarity to it. You can see that you've ended up just a little bit below where you started, so that negative sign makes sense. Abby, both answers are the exact same, which is kind of a funny thing in physics. So you could write negative 1.5 meters, or you could write 1.5 meters south. They both mean the exact same thing, which is the really kind of weird, interesting part of physics. We'll talk a little bit more about it later on. Negative signs indicate direction in physics. So both are the same. 1.5 meters south or negative 1.5 meters, both the same. Doesn't matter. Both are going to give you the correct answer. We'll look more into it later. So I don't have the learning guide with me. I'm just going to jump into the class here and grab it. And then we'll see how far we finished. I'll continue on with this stuff next day. All right, Unit 8 Learning Guide. Taylor, you asked a question number 10 on page 2. Let's have a look at that. Can three parallel vectors unequal magnitude add to 0? That's a good question. Draw a picture for that for sure. Can vectors different magnitudes and directions add to 0? Show with a vector diagram. Delta symbol we didn't really get to yet. We did these in class. And this is really similar to the question we just did. 4 meters north, 7 meters south, 2.5 meters south, and 5 meters north. So see what you can do there. Maybe now that I've done that example, Taylor, you may be a bit more prepared to do that. I'll maybe take it up next day. And if you guys have some questions with this sort of stuff, yeah, so we should be okay up to velocity. I'll do a few more questions next day in class, following through the notes. And if you guys go up to the velocity section, you should be okay. We haven't talked about velocity yet. So just kind of bounce back and forth between the questions because we have not learned it all. I'm thinking you guys have learned it all, to be honest. There'll be a few questions where you'll end up with maybe not seeing an example that's really similar to it, but if you use the sort of the concepts we talked about, you should be okay. I apologize for taking so long today. No, we don't normally take quite as long without sort of breaks, but hopefully you guys are okay. Just try. That's all I'm asking you guys for now. Try to do everything you can up to the end of the velocity, or up to the velocity, not to the end of the velocity. So you're going just into the middle of page 3. Do what you can. I will go through the rest of the questions in the learning guide or in my notes, which aren't the same as the learning guide, but similar. I'll go through the rest of the questions at the beginning of next class. If you guys have any other questions from the learning guide, I will go through those as well. And that's kind of where we're at. So I want you guys to just try. That's all I'm asking right now is just try. And if you are doing okay, then great. If not, we'll spend some more time on it next day. That's kind of it for now. Thanks very much. I will see you guys on Wednesday. Have a great afternoon.